what is regression discontinuity design? It's a way of undertaking causal inference. So what is the impact of something on something else using data? And it is usually used when you're studying some kind of policy intervention, but actually I would urge you to think of it as being more generally applicable to other areas where you are trying to find out about causal relationships. The good thing about it is that under fairly weak conditions or fairly minimal assumptions, it can provide robust, convincing estimates of causal impacts. So, it might compare more favorably than an estimate based on propensity score matching, for example. I'm an economist and Pepper is all economists, and we should freely admit that this method was invented about 30 or 40 years ago by psychologists, but economists, particularly labour economists, are now realising how applicable it is, and there's been a huge surge in economics of articles using regression discontinuity in the last 7 or 8 years, and you'll see that at the end most of my citations are from the late 2000s, and I suspect it is a method which is less well known outside psychology in economics, but there is no good reason for this whatsoever, and so hence the point of the day. Now, regression discontinuity is not going to be a silver bullet. So you can't just say, okay, I really want to know the impact of this thing on that thing. I'm worried about causality. Okay, I'm going to use regression discontinuity. You can't always do that. Whether you can use a regression discontinuity will depend entirely upon two things. First of all, the nature of the intervention. Some kind of policy interventions are amenable to being studied using a regression discontinuity, and other kinds just aren't, full stop. So if you're looking at those second kind, then go and search for another method. The second consideration is whether you've got enough data. So even if you think you are studying a policy intervention which is amenable to the regression discontinuity design, as I will go on to show, the data demands are often great, and it just may be that your data set isn't up to it. In other words, you don't have enough power in your data set to find the kind of impacts you're looking for. All right, so when is it appropriate? When might you be able to use a regression discontinuity? Well, this is a little bit formal. So what we're thinking about is an instance where there is some kind of treatment, to use the medical term, or some kind of intervention, or some kind of policy regime, intervention, which is given to some people and not to others. And the people who get it, they have some characteristic which lies to one side of a sharp cutoff. So there is some characteristic which we can measure. Maybe it's your date of birth. And if you are born before a certain date, then you get this policy. And if you're born after a certain date, you don't get the policy. That's a discontinuity. Okay, there's a cutoff there, defined according to your date of birth, and it produces a discontinuity. Also, it needs to be, this characteristic cannot be perfectly manipulated by individuals. Now, I just gave date of birth as an example, and of course date of birth cannot be manipulated at all, but in a minute I will show you some more examples, and it needs to be the case that this characteristic can't be perfectly manipulated, otherwise we might worry that people who particularly want or particularly don't want this policy intervention are just going to manipulate this characteristic so they fall the right side of the discontinuity. So this is why the method is not always applicable. I mean, if you have a policy which is given out universally to the entire population, you haven't got a discontinuity. Or if you have a policy where people have to kind of clear some threshold in order to get the policy or intervention, but they can manipulate that perfectly, then you haven't got a discontinuity. But if you have, then you may be in luck. So let me try and show this graphically. So on this axis, I'm going to show the jargon is the running variable. So this is the characteristic which determines whether or not you might get the treatment. It's called the running variable. I'm going to call it X. And there is a cutoff here, which I'm going to call C. And just to draw what I've described to you, the idea is that if you have a value of the running variable below C, you do not get the treatment. This is whether or not you get the treatment, 0 or 1. And if the value of your characteristic is above the discontinuity, you do get the treatment. Describing regression discontinuity is full of gestures. I mean, when I was first taught it by a famous economist, they basically just did this. That's all that. That is regression discontinuity. Okay, so this is a graph that's just illustrating, what are the conditions under which a regression discontinuity might be applicable. But then, why is it so good? Okay, so suppose we are trying to estimate the impact of this particular treatment on these people. These people are blue because they are being affected by the treatment. They're above the cutoff, sorry, they get the treatment. We want to know what the impact of the treatment was on these people. So in general, we would need to know what the counterfactual is. What would these people's outcome have been had they not been exposed to the treatment? Another way, we need a comparison group, is another way of putting that. Now, an ideal comparison group would be somebody or some people who have the same values of this characteristic, so they're similar to these people, but they don't get the treatment. And under various conditions, that would be an ideal comparison group, and we could just compare outcomes for the two groups, so we could get a nice causal estimate of the impact of the program. But in the situation I've described, those people don't exist. Okay, everybody who has a value of x above c is treated. But we have some people who have a value of x just below c who are not exposed to the treatment. And the basic idea of regression discontinuity is that if we look very, very, very close to the cutoff, we can find people who have a value of x not that different from another person, but who have different treatment statuses. Okay, so if you're x plus epsilon you're treated, c plus epsilon you are treated, and c minus epsilon you are not treated. And in principle, if x really is a nice continuous variable and we have masses of data, you can find two people with arbitrarily close values of x, but who are treated differently. And so the argument goes is that the red person just below the cutoff is a really good comparison for the blue person just above the cutoff. Sorry, my voice is going a bit after talking too much today. So to put that in writing, what you do then is you compare the treated outcome, so the outcome for somebody who's treated just above the cutoff, with the untreated outcome for someone just below the cutoff. And that basically will give you an estimate of the impact of the program. I would hope the way I've described it makes it seem very intuitive and very plausible. But there is a catch, and the catch is that really all you're doing there is you are indeed estimating the average impact of the treatment, but only for a very select group of people. You're only really estimating it for the people who are very, very close to the cutoff. Okay, so go back to the graph. I said that this red person is very similar to this blue person, but he's not very similar to this blue person, and it's certainly nothing like the blue person up here that I haven't drawn. So we're only really learning about the impact of the treatment for people who have a value of x very, very close to c. And if you suspect that the impact of a treatment depends upon the running variable, then there's more to be learnt. You haven't answered. You've not got a complete answer to the question what impact does the treatment has. Instead, you've got a robust and reliable answer to a very small question, or what might be a very small question. Now, things might not be as bleak as that. Perhaps you have good reason to think that the impact of the treatment doesn't vary very much with x, in which case you've learnt something more powerful. But formally, all you've really learnt is, to use the jargon, the average treatment effect for those people who are around the cutoff. I guess I'll pause in case anyone wants to ask a question or say anything. I should say I would also like you to interrupt as I'm going along. Yes?
Could there be multiple cutoffs? I was thinking of the example, for example, flu jabs, and you have the very young and the elderly who get the treatment. There's a limited amount available, and your running variable would be incidence of flu or something like that. That depends on...
No, your running variable is age. Because age determines whether you get a flu jab. Is that right? Is that where you're going?
Yeah.
Whereas a 15-year-old gets a free jab and a 16-year-old doesn't get a free jab. Right. And a 59-year-old does not get a...
You're looking at the outcome, which would be incidence.
So the outcome would be whether you get the flu.
Yeah.
Multiple cutoffs are good, but that's basically, you're asking two different questions. What's the impact of being offered a flu jab on someone roughly 16, and what's the impact of the flu jab on somebody roughly 60, if those are the two cutoffs? I'm making this up. But multiple cutoffs are good because you don't need multiple cutoffs, but it's fine to have them, and it actually can help because if you've got multiple cutoffs and you can find an impact consistently at all of them, then that's sort of giving you more confidence that what you found is real and not artificial. Which is basically the whole trick to this method, is convincing the reader that what you found is real and not artificial, because data gets in the way. Okay. Any others? Yes, Graham.
So some sort of entitlements are like tapered.
Yes.
So you're just saying that's
No, we need a discontinuity here. It's got to be a jump. I mean, and actually, at the end of the talk, I will talk about things where the discontinuity is a bit fuzzy. But for now, I really do mean that it's, you get the treatment if and only if you have a value of x just above c. Because we are comparing people just above c and just below c. Okay, I'll carry on. Why does this work? I'm going to be a little bit informal here. And actually, I think it's very easy to give the intuition. It's quite hard to explain actually why it works. But actually, there is an important assumption here that the running variable cannot be perfectly manipulated. And if the running variable can't be perfectly manipulated, then what happens is that individuals who are on either side of the cutoff should be very similar to each other, not just in terms of the x, the running variable, but also in terms of all the other things that you can't measure and would like to measure, and which might affect the outcome of interest. So it's not just that a 15-year-old and a 16-year-old are close in age. They're also similar to each other in all the other things which might determine whether or not they get the flu. That's the kind of idea to use that example. On the other hand, if the running variable could be perfectly manipulated, so age won't work, then that assumption would not be the case. It might be that people who particularly want to get the treatment will just ensure that they have a value of x above the cutoff. And those kind of people might well be different for people below the cutoff. Okay, so we need this assumption for technical reasons. But then basically what the situation you're in is that in a very small area around this discontinuity, it is as if you randomly assigned the treatment. Somebody with a value of x just below c is so similar to somebody with a value of x just above c, it is as if you took the two and flipped a coin to decide which of them got the treatment. And random assignment is kind of the ideal situation to be in when you're trying to work out the causal impact of a policy. I'm not saying it's the ideal way to pilot a policy, but it's the ideal situation to be in if you're trying to evaluate a policy. Yeah.
What would be a good variable?
Sorry, say it again?
Can you give me one example of a good variable? Because it's like when you are applying a policy, how do you decide who gets the subsidy?
Well, I mean, if you're analysing a policy ex post after the fact, you were just given this policy and asked to evaluate it, it either will or won't be appropriate to use regression discontinuity. You just need to think about how the policy was implemented. And in some cases, these cutoffs are deliberate, some cases they're accidental. Something we might have got into at the end is using spatial discontinuities. It either happened or it didn't happen. The question at the front was about the flu jab. It just happens that the NHS gives free flu jabs according to your age. So that means we automatically think of a regression discontinuity. Well, I do, because I always think about cutoffs. But if the NHS had said, actually, it depends upon other things like, other things, and it was a kind of gradual taper thing, or due to your propensity, or whatever, then this wouldn't be appropriate. So you can't manufacture a discontinuity if one didn't exist originally, but sometimes a policymaker might not have intended there to be a discontinuity, but there is one there by accident. Okay, and that's what I would urge you to think about. Okay, yes, the problem about having animated slides. There is, of course, another assumption, which is that nothing else is jumping at the cutoff. And that's, if other things are changing when x hits c, other than people getting a treatment, then that means you can't do causal analysis. Okay. All right, here are some more examples. Here are some real examples of studies that people have done using a discontinuity. So let's read it kind of from left to right. So people have looked at the impact of a school being placed in remedial measures on its subsequent exam results. So here the idea was that it's not from the UK, but if a school did particularly badly, government came in and kind of subjected it to remedial measures, and I guess it's not Ofsted, and you want to know whether these remedial measures actually help the school's subsequent performance. So, and in the country where the study came from, whether or not you got these remedial measures was a very, very strict function of your average exam results. So the idea is you compare a school that was just bad enough to be in this category with a school that was just good enough to not be in this category. Okay, and the idea is those schools should be basically equivalent to each other, except that one of them went on to get the remedial measures.
Do you want to say the country or not?
I can't remember what the country is. I just know it's not the UK.
It sounds like the Netherlands.
Okay, maybe, yeah, maybe. Lots of US studies looking at the impact of getting scholarships to go to university on subsequent, that should be kind of graduation results, where the scholarship is based strictly on your grade point average. So you just compare students above and below the cutoff. Lots of labour market or welfare to work policies depend upon your age or your date of birth, and that's what I'm most used to. Also, one thing I've done myself is looking at the impact of enrolling children in full-time school. The study I was looking at was, well, does having your child start school make it easier for the mother to go to work amongst young children? Well, in large parts of England, when you start school, depends upon your date of birth. You start school the 1st September after you turn 4. And so you can compare children born in September to children born in August when they are 4, and the August-borns will be in school and the September-borns will not be in school, but they're basically the same age. And you can look, so I looked at the impact of that on whether the mothers did work more, and they did. Actually, this is a good example to talk about the data requirements. So the study I did was impossible to do with household survey data because you just don't get enough mothers of 4-year-olds in household surveys, but I used administrative data on a particular known parents receiving welfare benefits, so I had about 50,000 children, mothers of lone mothers of children. Yes, lots of employment regulations or payroll taxes depend upon the size of a firm, so you might compare firms either side of that discontinuity, although here you might worry that how big a firm is actually completely within a firm's control. I mean, surely a firm can decide how many employees it has. And today we would worry that one of the assumptions is going wrong. And a really interesting one from outside economics is the impact of being elected to public office or being an MP, taking advantage of the fact that there's a discontinuity at 50% in a two-candidate race. So a study I might talk about at the end compares MPs it compares politicians who got 50.1% of the vote with those that got 49.9% of the vote, and looks at what happened to them subsequently. So those are some real examples. Any questions on those? Okay.
Sorry, Mike.
Yes.
All of those seem quite objective measures, like they're
the running variable,
yes.
Or yes, apart from firm size. No, this running variable's got to be something that's measurable.
Yeah. Okay.
So, well, I mean, I'm not sure if that's what you mean by objective. So you've got to be able to measure it. You have to be able to measure it. Yes. And some of these are deliberate discontinuities. You have to get a good grade to get a scholarship. You have to be a bad school to get remedial measures. Although others were sort of accidental ones. Like this one is basically government doesn't want to bother small firms because they're not worth the bother. So it just says, okay, if you're small, we'll ignore you. That's what it's trying to do. But then it's got to think of, well, where do I draw the line? And it draws a line, and that creates discontinuity. So I call that almost an accidental one. And this one is also an accidental one. Children have to start school at some point. It just happens that the way in parts of England, the way we set the rules up means there's a nice 1-year difference in when you start school for children born a day apart. Sorry, one day difference in date of birth means 1 year difference in starting school. So that's, what next is how do you do it? And if you read papers which are taking an RD approach, you will find a lot of graphs in them. And it's certainly where you should start as a researcher with looking at your data. So the obvious graph to plot is just what is the outcome against your running variable, either side of the cutoff. Okay? Here is a famous, well-cited example. You can see it's only 5 years old in the literature, but this is still one of the kind of important papers in economics using this design. So what's this particular paper? This particular paper is trying to work out what's the link between, what's the link between how long you're allowed to claim unemployment benefit and the length of time you spend unemployed. Now in the UK you get unemployment benefit for 26 weeks, no matter who you are, but in other countries they get much longer. And it happens that in Austria, the number of weeks you are allowed to claim unemployment benefit goes up at the age of 50. So if you're over 50, you are allowed to receive unemployment benefit for much longer than if you are 49. And this allows us to get at the general question, what is the link between how long you may claim unemployment benefit and your subsequent time in unemployment? Okay, so the graph just shows how many weeks you actually spent in unemployment against your age. And the dots are averages, I think, by by your age measured in quarters. So it's kind of 4 dots per year. And the dotted line is just an OLS, a linear fit between those lines. And this is purely raw data. I mean, it's based on a huge data set, but all the researcher has done is plot the average, the mean duration, the mean time in unemployment for people who started an unemployment spell at different ages. And you always, let's put it frankly, journal editors want you to show this graph, because if you can't see the discontinuity here, they're not going to be persuaded by the fancy statistics which follow. And you can see, so one of the nice things about this graph, the first nice thing is that this is quite a nice straight line. There's not much noise in this. This is pretty well estimated straight line, and this is fairly well estimated straight line. And the jump here is just much, much, much bigger than any other quarter-on-quarter jump. I mean, that's not a formal statistical test. Again, this is just looking at this thing visually. And for women, it's just absolutely extraordinary. And the impact there of, I'm afraid, you get an extra 170. You're allowed to claim unemployment for an extra 170 weeks, and that increases their time on unemployment benefit by an extra 100 weeks. It's not quite 1 for 1, but that's an enormous response. So the first step is just to draw a graph. No statistics, just average outcome by running variable, and just look to see whether there is a discontinuity. Now, there is actually a trick to this, and the trick is to put in this line and change the color as well. There are definitely some visual things, some graphical things going to make you think there is a discontinuity. All right, then, so having done the graph, and hopefully with the persuasive graph, you then go to do your formal estimate. I'm sorry, this is going to get a little bit more technical. And you have 2 choices. You can either do this parametrically or non-parametrically. What do I mean by parametrically? I just mean least squares. Estimate an ordinary least squares regression. What do I mean by non-parametrically? I mean apply a non-parametric estimator, which is usually a local linear regression. I'm not going to say any more about that. I'm just going to focus on the OLS case, because you don't need the fancy statistics to do regression discontinuity. What you need is the policy which has the discontinuity in it. So here is the regression that you would want to estimate. We have some outcome variable y that we care about. The key variable in our regression is an indicator I for whether your value of x is bigger than the running variable, the cutoff c. So tau is the thing we care about. So we're going to regress the outcome on a constant plus an indicator for whether or not you're above or below the threshold. Then jump to the bottom, we might put in some other explanatory variables that we also measure. You don't need these, but if you've got some other variables, individual characteristics, then stick them in as well. The important bit is the kind of bit in the middle, and this is a bit of a mess of algebra, but it's basically what this is actually doing is allowing for a quadratic relationship between the running variable and the coefficient of interest, where the quadratic relationship is different either side of the cutoff. Okay, so this is basically, that's why I've got abs for absolute value, and I've got indicator variables, whether it's above. So basically these 2 numbers, beta left 1, beta left 2, are the 2 coefficients in the quadratic relationship for values of x below the cutoff, and beta right 1 and beta right 2 are the 2 coefficients in the quadratic relationship for x above the cutoff. So you might estimate an equation like this, and then all you care about is the parameter tau. There we go. Yes, one more technical thing to do is if you do this, and you ought to allow for your errors to be clustered at the level of the running variable. So if x is measuring age in years, then you should cluster your error at the level of years. Okay, so that is the formal estimate. And I wanted to put the algebra just to convince those of you who know what OLS is about that it really is that easy. But then having done that regression, hopefully got a nice estimate, you need to do your sensitivities and robustness checks. And for some reason, these seem to be even more important when you're doing an RD design than in other areas of applied work. And it might just be because the first people that published papers in this area did a certain kind of test. It now seems to be almost compulsory just to do the same tests. Even though I had one referee tell me, there's no point to your tests. They have no power. Why are you doing them? Well, I was just following the literature. But here are the things you need to worry about at least, and you can decide what's the best way of testing for them. So you need to worry that something other than the treatment is causing these jumps. That's the obvious thing you've got to worry about. What people usually do to sort of check, to test this, is look whether other things are jumping at the cutoff. Well, what other things might you look at? Well, if you can measure your measure your outcome before the treatment happened, if you've got nice longitudinal data, you might look to see whether those pre-treatment variables jumped at the cutoff. That doesn't always happen. Often you have other explanatory variables which you might want to put in the right-hand side of your regression, and you should look to see whether those jump at the cutoff. Right, and they shouldn't. If they do, then that's warning you that there's probably something else going on causing around the cutoff. So you want to find, nothing here.
Sorry, can I just ask?
Yes.
If you do find that that's happening, but you're still including those as covariates, say you find something that does jump a little bit.
Yeah.
Does that factor out?
Right. Yes, formally it does. But the worrying, if you can't think of a good reason why your explanatory variables do jump at the cutoff, it's probably sending you a warning that there is something else going on at the cutoff that you haven't thought about and which you aren't controlling for.
Maybe a third variable.
Yes. But but also don't forget that sometimes things just do jump by chance. And let's say you had 100, if you had 100 of these and 5 of them jumped by chance, you shouldn't be worried. Okay, the second thing you might want to worry about is that, yes, individuals control the running variable. Okay, and there are 2 things that people do to look for this. The second one is what we've already had. I mean, that's why this is not a particularly good test, because you can look at it to see whether these things change at the cutoff, but if they do, it doesn't tell you what to do about it. So the second thing to do is the same as what we're talking about. The first one is, the new thing you do is look at the density of the running variable around the cutoff and look to see whether it's smooth. In other words, do you have basically the same number of people with a value of x just below c as you do just above c? And ideally you do. Okay, and if you don't, it's perhaps sending you a worrying sign. And let me show you a graph from a paper which did do this and found a worrying sign. So actually this is from a paper which sets out a formal test for this. But again, you can just do it by eye. So this is, the axis here, the running variable is the percent of what are they in the House of Representatives? Senators? The proportion of people in the House of Representatives who voted for a particular bill. So that varies from 0 to 1, and there's obviously a discontinuity at 0.5, because you've got to get more than half the voters to vote for it to be passed. And the hope was that people, I don't know why they were doing this, they wanted to study bills which only just passed with bills that only just failed. Okay, I don't remember why, but that was the intent of the study. But if they took data on hundreds of bills and the fraction who voted for them, and then just kind of try and plot the density, you can see that there is something weird going on here. And in particular, basically, there are just not enough bills that only just fail to get passed. Now, I'm not a political scientist, so I don't know what the reason for that is, but I mean, you can imagine that there are stories which might explain this. Maybe if you're the proponent of a bill and you can see it's going to fail, perhaps you decide to withdraw it. Whereas if you think you might get lucky, you don't withdraw it. Maybe there's this horse trading going on at the last minute. But there are lots of reasons which might explain it. About it, whatever they are, whatever is going on, it does look a little bit odd. And so this should send a warning signal to you that it might not be appropriate to compare those bills which just failed with those bills that just passed. Okay? So that's the density of the running variable. And my own study looking at a date of birth of children and whether mothers went to work. So we looked at the number of children born on each day in July, August, September, and October, and we found a dip in the number of children born in the last week of August, which is really problematic for our study. Now we thought for a bit, and we thought, well, I don't think it's people timing their births, because these are a fairly deprived, low-educated group. It's not pushy middle-class mums timing their births for September. This is a relatively deprived group. What could be going on? Then we remembered that giving birth is not a 7-day-a-week, 24-hour thing. It's a Monday to Friday, 9 to 5 activity, and it doesn't happen on bank holidays either. So when we stripped out the day, the week effect and bank holiday effect, actually it turns out that yes, fewer babies are born right at the end of August, but it's because there's a bank holiday. And in our sample, there was a weekend as well. So we think we're okay there. The final thing you need to worry about, and this is probably the most important, is distinguishing between a discontinuity and a nonlinearity. So the idea, what you're trying to do is that. When you're doing a regression discontinuity study, you're trying to spot the discontinuity in the outcome variable, but using statistical methods. But it can be hard to distinguish between discontinuity and a nonlinearity. Let me show you the graph first of all. So this is from mostly harmless econometrics, fake data. So the top slide shows you kind of the ideal situation where your data show there's a nice linear relationship between x and the outcome. There's a bit of noise around the linear, but it's clearly linear, and there's a jump, a clear jump. So RDD is going to work nicely there. Here there's a nonlinear relationship, but also a jump. And this will probably work provided you allow for there to be a quadratic response function, more jargon, above and below the cutoff, which was what I did when I showed you that OLS regression. I was allowing for there to be a quadratic relationship before and after. But the bottom one is a problem. So in the bottom, the graph has been drawn with no discontinuity in it. This is a smooth function of the outcome against the running variable, but it's got it's particular kind of nonlinearity. It's clearly not a quadratic. And hopefully you can see that if you were just to focus on, if you were to focus on data very close to the discontinuity, you might stand a good hope of spotting there isn't a discontinuity, because you don't hopefully estimate that straight line there. But if you were to focus on the whole span of data, and you were to say, I'm pretty sure the relationship between x and the outcome is linear, then you would estimate a straight line here, and a straight line there, and a very significant discontinuity there. Okay, so that's when, that would happen. So what could you do to protect yourselves against that? Typically then you would see whether your results in the OLS regression are robust to including higher order polynomials. So you might start with linear and then go quadratic, cubic, quartic, and so on and so on. And as you add more and more terms, you might find your standard errors blowing up, but you hopefully should find that your point estimate is not changing. And the second one is, are your results robust to changing the window around the cutoff? So I've just showed you how changing the window might affect your results. If you take ideally you want to use as small a window as possible, because the theory motivating this, the idea motivating this was that we're going to compare people who are very, very similar to each other. And obviously the bigger the window, the bigger the span of data, the more and more different people are going to be. And there's an obvious temptation to start off with as little data as you can get away with. In other words, you start with a tiny window and you make it bigger and bigger and bigger until your standard errors get smaller and smaller and smaller until finally you get a p-value of 0.05 and then you stop. Then that obviously would be a terrible thing to do. What you must do is you pick different size windows, pick sensible, objective windows. And you'll probably find that with a very small window, your standard errors will blow up and it won't be significant. But if the point estimate is relatively constant across all these different windows, then you've got a chance of arguing that you found the discontinuity rather than a nonlinearity. Okay, I'm running out of energy. Any questions? I've got 2 more slides which are about a variant on this, a more technical variant. So now's a good time for a question. Yes.
You mentioned clustering of the errors, and I was wondering whether that's something, whether you assess the clustering of the errors now, or whether
No.
cluster it yourself. What does that? What's it?
Well, I mean, in practice, I just mean you type. You allow for your errors to be clustered when you calculate the standard errors, which is usually a simple option in Stata or SPSS. There's a reason why you do that, which I'm not going to be able to explain to this audience, but I can tell you afterwards. And I'll give the reference at the end for why you should do that. I mean, it's kind of a recognition that even if you have a massive sample, all you're really doing is comparing people with the same value of the running variable to with other values of the running variable. So it's kind of like the do you aggregate or do you not aggregate question if you have grouped data. Yeah, grouped data. Okay, any others?
I've got one, but I think it takes us kind of into evaluation policy. So
well, this is all right. I'll do the variant then. I think this is important as well. So everything I've been talking about so far has technically been about something called a sharp regression discontinuity. And in other words, a situation where people get the treatment if and only if the value of x is above the cutoff. And actually it's quite hard to find policies like that. What is more common is where the chance that somebody is treated changes discontinuously when you cross the cutoff. It doesn't go from 0 to 1, the probability, maybe it goes from quarter to 3/4. For example, to take my children in school example, somebody who is a child born in September who is age 4 will not be in state-funded school in England, but their parents have the right to take them to a private school. So being born either side of discontinuity is not a perfect predictor of whether you're in school, but it's going to be a good predictor. And there's going to be a I look at data and there is a discontinuous jump in the probability that you are in some kind of school when you cross that cutoff. It might look like this. So here is we've still got a running variable. Here now we've got a probability of being treated, a chance of being treated, and it has a discontinuity. Okay, so if that is a situation that describes a fuzzy regression discontinuity. Yes, I'm not going to go through that. This one gets a bit harder to explain intuitively, and I have to use statistical jargon. But if you're in this situation, then essentially you have an instrument, a valid instrumental variable. So being on the right side of the cutoff turns out to be a valid instrumental variable, which you can then use. What do we mean by an instrumental variable? It's something that predicts well whether or not you get the treatment and has no direct impact on the outcome of interest. So in my case, being born in August and you're being aged roughly 4 is a really good predictor of whether you're in school. It's not a perfect predictor, but it's a very good predictor, and there's discontinuity. And it has whether being born in August has no direct impact on whether your mother works or not, compared to being born in September. And so you can then use standard instrumental variables techniques, and often it's just two-stage least squares, which I hope is a technique common to most quantitative researchers, where basically you look at the change in the outcome for people either side of the cutoff, and you divide that by the change in the treatment either side of the cutoff. You're basically scaling the change in the outcome by the change in the fraction of people who actually got the treatment effect. And that recovers the true causal impact. And there's a bit of technicality which will make sense to those of you who were at this morning's Pepper session. That's okay, that is it. So my summary then is that RDDs can provide convincing causal estimates and can be easily implemented using OLS. But they're not a silver bullet because it just depends on whether your intervention has these discontinuities in it. And even if it does, you're going to need large amounts of data. And I will leave you with a few references. It all came from Thistlethwaite and Campbell. It's 52 years old now. The economics literature is much, much more recent. Angrist and Pishka have a very nice chapter on it. That is a very accessible article. There's a whole special edition of this journal about it, which I've cited from regularly, and a couple of non-economics examples. So one is from health, and one is from political science.